This blood-red liquid can burn your skin, and even its fumes can damage your lungs. But here's the twist. This same chemical helps millions of lives every single day.
Welcome to our deep dive. Today we're digging into a really fascinating stack of chemical and historical fact sheets, all focused on a single topic, which is element 35 on the periodic table, bromine.
Yeah, and it's quite the topic.
It really is. Our mission for today's deep dive is to basically take these sources and figure out how one of the most toxic, just foul-smelling liquids on Earth operates as this secret, invisible workhorse in our modern world.
Because it is a massive contradiction when you really look at it.
Right. And to understand why it's such a contradiction, I want you, our listener, to just picture a desk, like a standard, everyday wooden desk.
Yeah.
And sitting right in the middle of it is a glass flask.
Okay, setting the scene.
Yeah. And inside that flask is this heavy, dark, reddish-brown liquid, bubbling slightly. And creeping out of the top of that flask are these thick, choking, intensely reddish-brown fumes.
Which is terrifying.
Exactly. And they're pouring out into the room, unprompted, right at room temperature. It honestly sounds like a supervillain's weapon from a sci-fi movie, like something designed to clear out a city block.
Oh, totally. It sounds completely made up, but it is an entirely real, natural element. And it is completely unforgiving.
Yeah, the sources make that very clear.
Oh, absolutely. When you look at the raw data in these chemical fact sheets, the defining characteristic of bromine is just how aggressively it behaves. I mean, it belongs to group 17 on the periodic table, which is a family of elements known as the halogens.
Right. And the halogens are, they're notorious in chemistry for being highly reactive. Right?
Very much so. They are not stable, quiet neighbors. You've got fluorine, chlorine, iodine. They all want to react. So understanding element 35 really requires balancing its intense physical dangers with its surprising utility.
You know, whenever you look at the periodic table, I think it helps to view it like a cast of characters.
Oh, I like that.
Yeah. You have your noble gases, which are, the elusive aristocrats that refuse to interact with anyone.
Yeah.
And you have your structural metals, the dependable, solid foundation.
And then you have bromine.
Exactly. Based on our sources, bromine is the ultimate rebel of the bunch. It completely refuses to play by the normal rules of physics.
It really does.
Out of all the nonmetals on the entire periodic table, bromine is the absolute only one that exists as a liquid at room temperature.
The only one. I mean, everything else in that non-metal category is either a solid, like carbon or sulfur, or gas, like oxygen.
Right.
And to understand how we eventually learn to harness this rebel, we first have to look at its bizarre physical state and the sheer shock of its discovery. Because for most of human history, it was completely hidden from us.
Yeah, the source material notes it wasn't isolated until 1826, right? By a French chemist named Antoine-Jérôme Balard.
Yes, Balard.
Yeah.
And in the early 19th century, discovering a new element was basically the pinnacle of a chemist's career. There was this intense scientific race to identify new elements.
But isolating bromine must have been a really different experience than finding, like, a shiny new metal.
Oh, completely.
I mean, Balard isolates this substance, and instead of a nice solid powder or some odorless gas, he gets this noxious, fuming, reddish-brown liquid with a deeply irritating odor.
The smell in that 1826 laboratory must have been overwhelming.
Yeah, actually, the odor is where it gets its name, right?
It is. It comes from the Greek word bromos, which literally means stench.
Wow, stench. That's telling.
Yeah, they didn't mince words. And the reason it produces that intense fuming stench really comes down to its incredibly narrow temperature window. The fact sheets list its melting point at minus 7.2 degrees Celsius.
Right.
But its boiling point is what really stands out. It boils at just 58.8 degrees Celsius.
Wait, 58.8? That's barely the temperature of a hot cup of coffee.
Exactly.
No wonder it's constantly emitting those fumes. If its boiling point is that low, is the liquid basically always trying to escape its physical state?
That underlying physics is exactly what drives its behavior. Boiling point isn't just a sudden switch, It's the temperature where the liquid's vapor pressure equals the atmospheric pressure around it.
Right, okay.
So because bromine's boiling point is so incredibly close to standard room temperature, the molecules inside that liquid have a tremendous amount of kinetic energy, even on a mild day.
So they're just bouncing around like crazy.
Exactly. They are energetic enough that they're constantly breaking free from the surface tension of the liquid. The liquid is continuously vaporizing into the air, creating that thick, reddish-brown gas you pictured earlier.
And the sources mention it naturally forms diatomic molecules, written as Br2.
Mm-hmm.
So it's vaporizing as pairs.
Right. In its natural elemental state, a single bromine atom is chemically unstable. So two bromine atoms will bond together, sharing electrons to form a single diatomic molecule, Br2.
Okay, got it.
And the bond between those two individual atoms is quite strong. However, the bonds between the molecules, like the forces holding all those Br2 pairs together in a liquid puddle, are very weak.
Oh, I see. So it takes almost no ambient heat to pull the molecules apart from each other and just send them drifting into the air as a gas.
Precisely. And those constantly escaping fumes explain exactly why bromine demands such intense respect in a lab.
Yeah, it's not just visually intimidating. It is aggressively hostile to human biology. The safety hazards listed in our sources are pretty severe.
Oh, they're terrifying. It is highly toxic and highly corrosive.
Like direct contact with liquid bromine causes severe chemical burns to the skin, right? And inhaling those vapors severely damages your respiratory system.
Yeah, handling it requires strict adherence to proper protective equipment. We are talking fume hoods, specialized gloves, highly controlled environments.
No messing around.
None. If those diatomic molecules enter your lungs, they begin reacting immediately with the moisture and the delicate cellular tissues, causing massive inflammation and damage.
But the danger isn't just in the fumes either. Let's talk about its physical presence, because the numbers here are wild.
They really are.
The fact sheets note bromine has an atomic mass of roughly 80 atomic mass units and a density of 3.12 grams per cubic centimeter.
Which is dense, very dense.
All right, to put that in plain English for you listening, water has a density of roughly 1 gram per cubic centimeter. That means bromine is over 3 times heavier than water.
Yeah, it's a shock to the system.
So imagine you're holding a standard plastic water bottle, but it's full of liquid bromine. It would feel incredibly heavy just sloshing around with this massive, unexpected weight, all while trying to eat right through the plastic and gas you.
That massive weight is why it violently subverts your expectations when you actually pick up a flask of it. Your brain expects the glass to weigh as much as water, but the sheer density catches you off guard.
So why is it so heavy?
It's all about atomic packing. Each bromine atom is packed with 35 protons and 45 neutrons, which gives it that high atomic mass. And those atoms pack relatively closely together in the liquid state.
So it's incredibly dense. But what drives the destructiveness? Like, why is it trying to eat through the plastic or burn human skin in the first place?
It goes right back to its identity as a halogen. Elements in group 17 have 7 electrons in their outermost shell.
Okay, 7, and they want 8, right?
Exactly. In chemistry, elements are constantly seeking stability, and true stability requires having 8 electrons in that outer shell. Bromine is 1 electron short. It is desperate for that final electron.
Ah, I see.
So when it comes into contact with biological tissues, it aggressively steals electrons from the molecules that make up your cells to form new compounds. It literally tears biological tissues apart at the molecular level just to satisfy its own chemical reactivity.
Wow. So it's a dense, heavy liquid that aggressively tears apart organic matter to steal electrons.
That's the rebel for you.
If bromine is this dangerous and this relentlessly reactive, it is a very good thing there aren't just, pools of pure liquid bromine lying around in nature.
Oh, thankfully, no.
Right. You don't just stumble upon a fuming red pond in the woods. So how does nature handle this element? Where is it actually found?
Well, nature basically keeps it safely locked away. You will find bromine naturally occurring in massive quantities in seawater, in underground brines, and in salt lakes, like the Dead Sea.
Okay, but not as a red liquid.
Right. In those environments, it does not exist as that free, fuming liquid. It is found safely bonded as bromide ions.
Let me make sure I understand the mechanics of that. I'm picturing this reactive element like a dangerous wild animal being safely locked in a cage.
Yeah.
But based on what you just said about the missing electron,
Yeah.
is it more like a wild animal that's finally been fed? Like, because it already stole the electron it desperately wanted from another element in the seawater, it's chemically satisfied.
That captures the molecular reality perfectly. The wild animal has been fed.
So it's only safe for us to swim in the ocean because the bromine has already completed its outer shell.
Exactly. In seawater, bromine has already interacted with elements like sodium or potassium, grabbed that missing electron, and formed stable, harmless bromide ions. They just float around in the ocean, completely benign.
That is wild to think about.
You interact with bromide ions every time you swim at the beach, and your body doesn't even notice.
But to use it in modern industry, we need the dangerous version, right? We have to actively intervene.
We do. Humanity has to actively mine those underground brines and salt lakes, pump the salt water into processing facilities, and put those bromide ions through intense chemical reactions.
Why do they do that?
Usually they introduce chlorine gas into the brine. Chlorine is actually higher up on the periodic table and even more reactive than bromine.
Oh, interesting.
So the chlorine violently forces the bromine to give up that extra electron. We strip the stability away, forcing the element back into its pure, heavy, fuming liquid state. We essentially unlock the cage.
Wow. The effort required to unlock that cage must mean it's incredibly valuable to us. I mean, we wouldn't go through the massive expense of mining salt lakes, introducing chlorine gas, and handling a toxic, lung-damaging liquid just for fun.
Definitely not.
It has to serve a major purpose.
It is absolutely foundational to the modern world. The range of industrial and scientific applications is staggering, and almost all of them rely on that exact aggressive reactivity we've been discussing.
Yeah, the sources list an amazing variety of uses. Bromine is used in water purification systems, swimming pool disinfectants, flame retardants, pharmaceuticals,
Even agricultural chemicals.
right, and photography, and as a drilling fluid for oil and gas exploration. I really want to unpack these because some of them seem entirely counterintuitive.
Oh, they definitely do.
Let's start with water purification. We just established that this is a highly toxic, corrosive chemical that causes severe respiratory damage and a horrific skin burns.
Yes.
And we use it to purify our drinking water and disinfect our swimming pools. How does a poison become a purifier?
It sounds like a total contradiction, I know.
Right.
But the lethal reactive nature it has toward human cells is the exact same mechanism that makes it devastatingly effective at destroying harmful pathogens in water.
Oh, right, because pathogens and bacteria are made of cells too.
Exactly. When scientists carefully control the dosage and the specific chemical form of bromine added to a swimming pool or a cooling tower, it behaves exactly as it does in our worst-case scenarios.
It violently reacts with organic materials, stealing electrons.
Yes, but in a treated pool, the organic material isn't your skin, it's the cell walls of harmful bacteria. Bromine tears the bacteria apart at the molecular level, neutralizing the threat.
So it's controlled destruction.
Precisely. Controlled destruction harnessed to protect human health.
Okay, the logic of controlled destruction makes perfect sense for killing bacteria. But the sources also list it as a crucial component in flame retardants.
Yes, very common application.
If it's tearing apart biological material in water, I'm struggling to see how that translates to a flame retardant. Fire isn't biological. Is it attacking the chemical structure of the fire itself?
That is exactly what it's doing. To understand how bromine stops a fire, you have to think about what fire actually is.
Okay.
Fire isn't just heat. It is a runaway chemical chain reaction.
Yep.
When heat is applied to a material, say the fabric of your couch or the plastic casing of your computer, that material begins to break down and release flammable gases. Those gases react with oxygen in the air, releasing highly reactive molecules called free radicals, which create more heat, releasing more gas, and the cycle just spirals out of control.
So it's a self-feeding loop of free radicals.
Right.
Where does bromine come in?
Well, manufacturers embed bromine compounds into the plastics and fabrics of everyday items. When those items heat up to a dangerous level, the bromine compounds intentionally break down, releasing active bromine atoms directly into the nascent flame.
Oh.
And because bromine is so incredibly reactive, those atoms intercept the free radicals in the fire. The bromine bonds with the flammable gases faster than the oxygen can. It essentially starves the chemical chain reaction.
That is brilliant engineering. It's
Yeah.
like throwing a chemical blanket over the fire at the molecular level.
Yeah.
It uses its natural desire to react to step in front of the oxygen and shut the whole loop down.
Exactly. We are using the rebel element to disrupt another rebellious reaction.
I love that. And we see another brilliant application of its reactivity in photography, right?
Yeah.
Specifically through compounds called silver bromide.
Yes, that's a classic one.
I noticed that in the source sheet. How does silver bromide work? Does it tie back to what we were saying earlier about the bromide ions being safely locked in a cage?
It ties back directly. If you've ever seen a traditional photograph develop in a darkroom, you are watching bromine chemistry at work. Silver bromide is a compound where silver and bromine have bonded together.
Okay, so the bromine has its extra electron. It's stable.
Right. But silver bromide is uniquely sensitive to light. When you coat photographic film with silver bromide and expose it to light by clicking a camera shutter, the physical energy from those photons of light hits the compound.
Let me guess. The energy from the light is enough to break the bond. it breaks the cage.
The light breaks the cage. The photon provides just enough energy to knock the electron around, severing the ionic bond between the silver and the bromine.
Wow.
This frees the silver atoms. The free silver atoms then cluster together on the film, turning dark and creating the physical pixels of the photographic image.
That is incredible.
Yeah, without the specific, delicate chemical balance of silver bromide, the entire history of 20th century photography, cinema, and even X-ray imaging just wouldn't exist as we know it.
It's amazing to think about. We take this heavy, fuming liquid, lock it in a chemical cage with silver, and use the energy of light to paint images with it. It gave us the ability to capture human history on film.
It really is beautiful when you think about it.
And then, jumping from the delicate art of photography to heavy, brutal industry, the sources mention its use as a drilling fluid for oil and gas exploration. I assume this relates to the density we discussed earlier.
It relies entirely on the density. When engineers are drilling deep into the Earth's crust for oil and gas, they are piercing highly pressurized environments.
Right.
The natural gases and fluids trapped underground want to violently rush up the drill hole, which can cause catastrophic blowouts. To prevent this, drillers pump specialized fluids down into the hole to exert downward pressure and keep the well stable.
And because bromine is over 3 times heavier than water, if you formulate a liquid using bromine compounds, it's going to act like a massive, heavy plug pressing down on the Earth.
Exactly. You can create clear brine fluids using bromine that are exceptionally heavy. They sink down the drill shaft and exert enormous hydrostatic pressure, holding back the forces of the Earth while the drill bit does its work safely.
We use its sheer physical mass to hold the ground in check.
Yes.
So we use its massive weight to hold down the Earth. We use its aggressive reactivity to tear apart harmful bacteria in our water. We use its chemical structure to intercept oxygen and stop fires. And we use its delicate light sensitivity to capture photographs.
Yeah, it is an absolute workhorse across completely different fields of science.
But an invisible one.
Yeah.
I mean, that is the great irony of bromine. Once we extract it from the salt lakes and process it, the general public almost never sees it in its pure, reddish-brown, fuming state.
No, outside of a highly controlled laboratory, it is completely hidden from view. You only ever experience the safety and convenience it provides through its specialized compounds.
And that really brings us full circle on this deep dive. We started with a vision of a strange, heavy, reddish-brown liquid bubbling on a desk. Element 35.
The stench.
The stench. First isolated in 1826, it is a foul-smelling, highly toxic halogen that boils at the temperature of a hot coffee and sits ready to aggressively tear apart organic tissue to steal electrons.
Right.
Yet despite being a genuine hazard to human life in its pure form, humanity learned to harness it. It works silently behind the scenes. It purifies the water you swim in. It protects the electronics in your home from bursting into flames. It provides life-saving pharmaceuticals, and it holds back the immense pressure of the Earth to help drill for energy.
It is the chemical rebel that we convinced to work for us.
It is a profound testament to the power of human ingenuity. Taking an element that is fundamentally hostile to biology, understanding its atomic structure well enough to manipulate it, and making it an indispensable pillar of modern safety.
Which is exactly why it's so important to study these things.
Absolutely. And that's exactly what we love unpacking here. Next time on our deep dive, we'll be looking at the next fascinating piece of the periodic puzzle. Make sure to follow, subscribe, and join Atomic 118 for more explorations into the elements that build our universe. We are going to cover every single element one by one.
But before you go, I want to leave you with a lingering thought about bromine's invisible presence in your daily life.
Oh, what's that?
Well, we spent a lot of time talking about how incredibly effective bromine compounds are as flame retardants in our everyday products, right? Our couches, our computers, our car seats.
Yep.
We also know that bromine is naturally toxic and relentlessly reactive in its pure form. So consider this. What happens to all those invisible bromine compounds when those everyday products eventually break down?
Oh.
Yeah, decades from now, and that computer casing or that couch is sitting in the landfill, degrading under the sun and rain, where do those highly reactive chemical rebels go? It's a vital reminder to question the unseen chemical footprints we leave behind in our relentless quest for safety and convenience.
That is definitely something to think about the next time you sit down on your couch or take a sip of purified water. Until next time, keep exploring.